Hello and welcome back to the second episode in my series, or I think what is a series at least, on Squircles. And you'll notice that the word Squircles really isn't on the screen except in the corner, and that the word Sphubes is out center, out front and center. And the reason for that is because in this video I would actually like to derive the formula for volume of a Sphube. I guess three dimensions is actually implied in that, but I'll say it anyway. Volume of a sphube or 3D Squircle in 3D. And I'd like to specify that because actually in the next video I'd like to do it in, say, M dimensions or D dimensions. We'll see what variable we end up using there. So yeah, anyway, we should probably get started. But first, before I begin, I would like to give y'all a little bit of intuition as to, what is what a sphube looks like. Uh, it's like it's kind of what you would expect. I'm gonna be honest. It's like a cube. It's also kind of like a sphere. Has the word sphube. Again, as n increases, it becomes more and more like a cube. And as you decrease n, it becomes more and more like a sphere, and then eventually becomes some other kind of wacky shapes. Like here you have, I forget the name of this shape, but it has however many sides. And if you decrease n even more, you get whatever that is. It's cool. That's not the point. We're just going to be driving the an expression for the volume. So it's probably about time to actually get started and not ranting, and that should actually be an n. I'm very sorry. Okay. On to the math. Okay, so our equation for a for a for a sphube is just x. Whoop. It's just going to be x to the n plus y to the n plus z to the n equals r to the n. And again, the reason why we can drop the absolute value signs is basically because we're only integrating, or we will only be integrating over the first quadrant, or octet, I guess, technically we're in 3D. We're only going to be integrating over the first octet, where x and y, and z for that matter, are all positive, so we can just kind of drop the absolute value signs. It's all good. I'm just going to solve for z real quick. It's just going to be r to the n minus x to the n minus y to the n to the 1 over n. Meaning that we can just do a double integral, find the volume. So 8 this time, because we have octets, times, and we're finding, and this double integral is going to give us like 1/8 of the volume, because again, here it's like we're finding like this chunk right here, like this chunk right here, and then we're just going to multiply that by 8. Let's see where that comes from. Bounds are still going to be, our lower bounds are still going to be 0, top one's going to be r. The other one, though, is actually going to be r to the n minus x to the n to the 1 over n. Reason being, actually, that if you actually kind of look here, if we take y to be 0, that's kind of what we're left with. Or, sorry, if you take z equal to be 0, that we're left with y equals that, and that's like our upper bound there. Yes, hopefully that makes sense. So, onto the actual integral bit. R to the n minus x to the n minus y to the n 1 over n dx. I don't like to, I'm gonna stop saying that now. I'm sorry. Okay, similar to last time, I'm going to factor some stuff out, but it's going to be slightly different stuff. It's going to be slightly different because you'll notice here that I wrote the what we're integrating with respect to wrong. You'll notice that we're actually only integrating with respect to y. So this, we have an x here, but like this, if we just focus on this integral here, x is just kind of like a constant. So what we're going to treat it as such, same as r actually. So what we're going to do is say, okay, well r to the n minus x to the n minus y to the n to 1 over n. Well, that is just equal to same thing as if we were to like factor it out. So what we're going to say is this is the same thing as r to the n minus x to the n to the 1 over n, but times 1 minus y to the n over x, or r to the n minus x to the n over n. Okay. Those are the same thing. Those two things are equivalent. So I'm just going to sub one in. And what you'll notice here is we don't get rid of that term completely, but we just kind of, it's almost like a form of procrastination. We're just gonna say we're gonna deal with this little part later in the integral. So r to the n minus x to the n to the 1 over n. And we just have 1 minus y to the n over r to the n minus x to the n to the 1 over n. I'm sorry, it's getting quite messy, but I promise it'll simplify. And what we're going to do here is very similar to what we did earlier, in the previous video at least, when we derived the volume of, or sorry, the area of a normal Squircle. We're just going to do a u sub here and use the gamma function. So we're going to say u is equal to y to the n over r to the n minus x to the n. And that du is equal to n y to the n minus 1 over r to the n minus x to the n dy, but then subbing in for our y, of course, we know that y is going to be equal to r to the n minus x to the, I think I'm saying to the n way too much, and I'm very sorry, but there's just a lot of exponents this time. And it is actually a tad bit annoying, perhaps, but I mean, it is what it is, you know, it's a Squircle video. So, u to the 1 over n. Okay, what we're going to do now is just sub this in. So, du is equal to n times, yeah. So y is just that, so we're going to have, u to the n minus 1 times 1. Oh, sorry, I need to actually look at this. r to the n minus x to the n times 1 over n. Sorry. N minus 1 over n. Apologies again. My gosh. Sorry, I don't know if y'all can hear my family's in the background doing, what. Probably yelling at me to get downstairs for dinner, but math. Okay. You will notice here actually that we can simplify this quite a bit. But that's unnaturally large dy. Okay. This exponent right here, actually, I'm going to rewrite this real quick as a 1 minus 1 over n. And the reason for that is because you'll notice we have this here. This is just to the first power. This and that just cancel. It's quite nice, actually. So we are left with, I'm going to solve for dy as well while I'm at it. So dy is equal to, its negative becomes a positive, so r to the n minus x to the n times 1 over n. All over n. And what we're going to get is a u to the 1 over n minus 1 du. Alright. That's a lot, I know. Geez, that's a very long u sub, yes. But what we're going to do actually is just, I'm going to plug that into there. So what we're going to get is, there should be dx there. I'm just going to focus on this first integral right here. So just know that what I'm writing now is actually still going to be integrated with respect to x. I'm just going to drop the notation a bit, just for the sake of brevity. So yes. So we have our integral still. I'm going to change the bounds real quick. So you'll actually notice that our bounds are from 0 to r to the n minus x to the n to the 1 over n. Speaking through that because it's just a mouthful. Raise that to the n power, it does actually cancel in our u right here. So our bounds are just from 0 to 1. And what we're going to do next is just sub everything in. So 1 minus u. We chose our u specifically to be that, so we don't have, so we can take advantage of the gamma function. And I am going to move this little term right here out to the outside. So r to the n minus x to the n, so 1 over n. I'm just moving that to the outside. We're only integrating with respect to y, if you remember. There's a 1 over n here. That'll get used whenever we start simplifying things. Don't worry about that for now. And then we have a u to the 1 over n minus 1 du. And you'll notice this looks a lot like the gamma function, which it is. So we know that we have that this little term right here is going to be equal to gamma of 1 over n plus 1 times gamma of 1 over n over gamma of 2 over n plus 1. So notice none of that depends on x. So we can actually just factor that entire thing out of our integral. So what we're going to do is, sorry, my sister's crying in the background. I'm very sorry if you can hear that. I don't want to hear it either, trust me. I'm sorry. Let's see, where was I? Yes, okay. 8 times the integral from 0 to r. Yeah, so what we had up here, which is going to be our r to the n minus x to the n to 1 over n. Notice that we have two versions of that, and we're multiplying both together, so that's going to be squared. So we're actually going to have an r to the n minus x to the n to the 2 over n dx. And then it's going to be multiplied by this whole monstrosity as well. And also be divided by n. So I'm just going to throw that out front. So gamma of 1 over n, gamma of 1 over n plus 1, gamma of 2 over n plus 1. There's an extra n out front. Yeah. I mean, you could simplify that now, but I'm just going to save it for the end. Just simplify everything in the end. Okay. So we just have this small, but actually somewhat daunting integral, perhaps. We're going to do it using the same method, actually. I'm going to factor out an r, and then we'll go from there using the beta function. So a lot of this might seem monotonous, but I promise this one is going to be different, and the end result is quite cool. So what we are going to do is just factor out the r. So x to the n, or r to the n minus x to the n to the 1 over n is equal to, let's see, sorry, r. Oh, I'm sorry, that should be a 2. My apologies. R times 1 minus x to the n over r to the n to the 2 over n. Actually, r squared, I'm sorry. And it's a squared because you have that 2 right there. So what we're going to have here is, I'm just going to sub this in real quick. The integral from 0 to r of r squared of 1 minus x to the n over r to the n to the 2 over n dx. Okay. And what I'm going to say here is u is going to equal to x to the n over r to the n. Very similar to the first video I did with Squircles, to the previous one. So this should hopefully be very familiar. So what we're going to have is the integral from 0 to 1. Those are our new bounds. R squared is still out front, but what we're going to have here is r du. It's going to equal to n. It's going to be equal to this. I'm not going to say it anymore. I'm tired of saying to the n minus 1. I'm sorry. I'm very sorry. I mean, it might be helpful, but I mean, it's a mouthful. Oh my goodness. Okay. I'm going to solve for x now. X equals r u to the 1 over n. Okay, my goodness. All right. And what we have here now is equal to n times r to the n minus 1 times x, I'm very sorry, u, the n minus 1 over n over r to the n. Notice that the r to the n's cancel. Very helpful, isn't it? So boop and boop. I'm just gonna solve for dx now. Dx therefore equals the inverse of that thing right there, so it's r over n times u to the 1 over n minus 1. So very similar to our first, so the first one. So we have an r, and then we have, I'm worried that we have an r squared and an r. I'll get into that, don't worry. We have an r over n times 1 minus u to the 2 over n times u to the 1 over n minus 1 to u. Alright, well, we can just use the beta function, can't we? So we have our gamma of 2 over n plus 1 times gamma of 1 over n. Now I'm just going to add the 2. Gamma of 3 over n plus 1. And then we have an r to the 3rd over n. But don't forget, we still had all that other gamma stuff right there. So I'm just gonna like add that in here. I'm rewriting it twice would be a whole lot. So we have gamma of 1 over n times gamma of 1 over n plus 1 over gamma of 2 over n plus 1. Then we had an extra n as well. Okay. So, you'll notice a few things actually do cancel. Namely, these terms. And that we have a 1 over n here, a 1 over n here, and a gamma of 1 over n there, a gamma of 1 over n there. Meaning that for each of them, we're just going to get one of these terms right here, meaning that that term is going to be raised to the 3rd power. That's quite fast. Hopefully you see what I mean. So basically, we have a 1 over n times a gamma of 1 over n, meaning that this is just gamma of 1 over n plus 1. We sub that in twice, right? And we end up eliminating the n's on the denominator, and we end up getting an r to the 3rd, gamma of 1 over n plus 1 to the 3rd power. The reason for that is because we have 1, 2, 3. Not so bad. And then we have a gamma of 3 over n plus 1. And then this is going to be equal to, I'm just going to put this in terms of factorials. Kind of makes it look a bit prettier, though. I guess if you want to impress someone, you can use the gamma function, but yeah, you know. So whatever. Oh, I forgot the 8. I'm very sorry. There should be an 8 there. There should be an 8 there. Okay. 8r squared times 1 over n. Factorial to the 3rd. Order matters. Times 3 over n factorial. And yeah, this is our formula for the volume of any sphube. Now, a couple of things you might actually notice. I know this video is going quite long. I'm sorry. But a couple of things you might notice. For our formula for the 2-dimensional, we had an r squared. For this one, we have an r to the 3rd, which is quite cool. In many ways, this actually kind of resembles, in a way, the formula for, say, a sphere, right? Because you have like this r to the 3rd term, and then you have some extra stuff. So, which makes sense, because if you plug in 2, this, should reduce to that. So, I think we'll do that in the next video, actually. Instead of generalizing this in m dimensions or something, I'm going to push that back one, and we'll just kind of do examples of like, okay, let's make sure this actually works. We're going to plug in 2, maybe plug in like, I don't know, 1, and maybe take the limit as it goes to infinity, just to get kind of a feel for what these formulas actually mean. So, yeah. That was a lot. I'm sorry if I said whatever to the n too many times. I really am sorry. But I hope y'all enjoyed, and yeah, catch you in the next one. Thank you for watching.